Hi everyone, today we're going to talk about 1.4, which is called dot product. So let's define what is a dot product. So as the name suggests, dot product is kind of like a product. So therefore it's kind of like the end result of a multiplication. However, as we already mentioned multiple times, we're not going to define a true multiplication between two vectors because when we multiply two vectors together, the result doesn't really have a good geometrical interpretation that we can use. However, this dot product is indeed a product between two vectors, just that the output is a little different. So show you the dot product between two vectors in Rn. So now as soon as I wrote this, you realize that dot product is a binary operation because it allows us to deal with two vectors. And those two vectors have to be in the same dimension Rn in order for it to work. So the dot product between two vectors in Rn is a scalar given by the following formula. So suppose I have these two vectors, vector x, which is x1, x2, dot, dot, dot to xn, and vector y, which is y1, y2, dot, dot, dot to yn. So in this case, both of these are basically using subscript notation, not the xyz notation. So suppose I have these two vectors, vector x and vector y. So what is the dot product between them? So the dot product between them is actually given by this symbol, which is basically a dot. So this is read x dot y, vector x dot vector y. Is this similar to when you put a dot to indicate multiplication? Yes. When you put a dot between two scalar, that indicate multiplication. But if you put a dot between two vector, that indicate dot product. And the nice thing about it is that dot product between two scalar is the same thing as multiplication between two scalar. That's the reason why the notation is used with multiplication with scalar. But do understand that for us, we'll use dot product only with vectors. So what is this formula going to state? The formula states the following. So if you do x dot y, that basically means x1, x2, dot, dot, dot to xn. Oops, xn. Dot product y1, y2, dot, dot, dot to yn. And the end result is going to come out to be x1, y1 plus x2, y2 plus dot, dot, dot plus xn, yn. Notice that this right here is a sum. Therefore, generate only a scalar. One of the most common mistakes students make is that sometimes they would give me an answer after a dot product and claim that the answer is a vector. It's not. Dot product only return a scalar. Right here. It's in its definition. You can only give a scalar. Okay? So keep that in mind. If you do try to do dot product between two vectors and you somehow tell me that the result is a vector also, then you told me that you don't. You're basically telling me that you don't understand how dot products work. So please don't do that. All right. So give you some example to see how that works out. So some of a very basic example. Let's say vector x is equal to -1, 3, and vector y is equal to 1, 2. So then let's see we can find vector x dot vector y. So therefore, vector x dot vector y would equal to -1, 3 dot product 1, 2. If you want to multiply two vectors together, you have to have that little dot right in between, because without that little dot, you try to tell me you're multiplying two vectors together, which we don't have such an operation. Excuse me. So how do you multiply, or how do you do a dot product between two vectors? You basically multiply the corresponding number together and then add them up. So don't forget to add them up. So I'm going to multiply the first number of both vectors together. So -1 times 1. And I'm going to add 3 times 2 because those are the two second number together. So that becomes -1 plus 6. So the answer is 5. There you go. Plain and simple. Okay, notice that your answer is a single number 5. Okay, not a vector, not the vector -1, 6, which a lot of students often put that down as the result of a dot product, but it's not, because dot product requires you to add each of the numbers together into a single scalar. Okay, another example. Find this. Okay, so I'm going to ask you to pause the video so that you can go and try it out. And then once you do it, you can kind of check my answers. Okay, so I'm going to continue. So if I do multiply this correctly, it will basically just be 1 times 2, which is 2, plus -2 times -1, which is 2, plus 0 times 7, which is 0, plus 1 times 5, which is 5. So that come out to be 9. Interesting thing to note is that first example is a dot product between two vectors in R2. The answer is a scalar. Guess what happened when you do a dot product between two vectors in R4? The answer is still a scalar. Okay, so that brings us to a very important concept. Okay, as you can see from these two examples, you should realize one very important thing is that dot products dot product is not closed. So therefore, what does that mean is that we actually cannot repeatedly multiply a whole bunch of vectors together through dot products. As a matter of fact, once you multiply two vectors together to form a scalar, you can no longer do dot product with the remaining vectors. So therefore, dot product is truly just a binary operation, and you can only do it with two vectors once, and that's it. So keep that in mind. So the next thing I want to talk to you about will be the following. Property of dot products. So even though dot product doesn't have the closure property, but it does have other properties that we can use because of the fact that, dot product and there are definitely properties that we can use. Some of them works and some of them are similar to a property you expect it would be true, while some of the other one you probably don't expect that. So let's see what happened here. So let's start with the following. Let's say given 3 different vectors x, y, and z in Rn, and let's say we have a scalar s. Actually, you know what? Let's use r because s look like 5. R. Dot product has the following properties. Number 1, if vector x is not the 0 vector, then when you do a vector dot product itself, you always get something greater than 0. Of course, in this scenario, if vector x is equal to 0 vector, then 0 vector dot 0 vector just equal to 0, of course. But if you don't have a 0 vector, then the dot product between a vector and itself must always be positive. Now, this actually is an interesting property, which actually mirror a property that we know in real numbers, is to say that if you don't have 0, if you square a number, you always get a positive number. So if x does not equal 0, x squared is always greater than 0. So here is kind of the same thing, and we actually kind of mirror this dot product, kind of like squaring. Okay, but of course it only works because you give out a scalar. Number 2. If you take vector x and you dot product vector y, it just so happened to be same thing as vector y dot vector x. So commutative property is actually true with dot product, and if you think about it, it kind of makes sense because the dot product requires nothing more than just multiplication and addition, which they're both commutative. Okay. And of course, when you try to add numbers together, and if some of them are negative, you don't consider them to be subtraction, but you consider to be adding the negative. And with that being said, something often also confused is that they think that dot product between two vectors is always positive. It's not true. Only a dot product of a vector with itself is always positive. But if you dot product between x, let's say x and y, then the result you could get is any number between negative infinity and positive infinity. It could be positive, could be negative, could even be zero. And we'll talk about the consequences of that later. Number 3. What if you have x plus y, then dot product vector z? Well, that is the same thing as vector x dot vector z plus vector y dot vector z. Now, because of the fact that dot product is commutative, you could easily have this, which basically means the same thing. And this statement is exactly the same as what's the one on top, because z dot x is the same as x dot z, and z dot y is the same as y dot z. Number 4. If I take a scalar and multiply by a vector, and then dot product another vector, what does that mean is that actually gives the same result as if you just take the dot product between the two vectors and then multiply by the scalar. And this is also exactly the same as if you do this. All three of them are exactly the same. Now, this is actually called a associative property. Very important to make sure you understand that, because some students would think that when they see this, they're thinking like, oh, isn't that like distributive property where you distribute R to both X and Y? No, because remember what I told you, distributive properties only work when you have a multiplication into an addition. Here is the multiplication into dot product, which dot product, as the name suggests, is more multiplication than anything else. So therefore, this is associative property, not distributive property, and you don't all of a sudden in the middle term right here create 2R, Rx dot Ry. That is incorrect, so don't do that. Okay. Now we can definitely prove some of these properties, but the properties proving these properties are actually very similar, pretty much the same exact thing as what we did before. So I will probably ask you to prove some of these properties also. So I'm going to strongly recommend that you try to do some of these on your own. Other than the first one, well, actually the first one you can also do that, but we kind of going to see how the first one work out right now. Other than the first one, 2, 3, and 4 are all very likely that I could ask you to prove on the test. So be careful. And if you want, we can definitely try to do one of them in class. Now, some of you at this point, usually at this point, there are students that are going to be thinking like, okay, that all seems okay. We seem like we have this operation and it is well defined. It is well defined and seems like there are properties of it, but why? Why do we define this operation the way it is? I mean, it is called dot product, but yet it's more like a product and an addition both together. So why do such a thing? That seems kind of weird. Well, there are many reasons why that is the case, and a lot of the reason why it is defined the way it is actually through economics, on how different variable work in a system that describe how like an economy work. So I obviously won't be able to get into why, but there is at least one geometrical interpretation of why dot product is defined this way and what's the purpose of it. So go ahead and show you. So one reason or one way to interpret dot product is to interpret dot product using a geometrical interpretation. Or at the very least kind of show you what does dot product do. And we later on we're going to look at a trigonometric interpretation of what dot product is. So let's say, for instance, suppose I do have a vector x, which is x1, x2, dot 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 to xn. And let's specify that this vector is not the zero vector. Okay? Then therefore, what happened is, if you think about it, if I take vector x dot itself, what would happen to it? So that would be just x1, x2, dot dot dot, xn, dot product x1, x2, dot dot dot, xn. And when I do that, I find out that x dot x is actually equal to x1 times x1, so it's x1 squared, plus x2 times x2, which is x2 squared, plus dot dot dot, plus xn times xn, which is xn squared. Now, one of the reasons why when you take a vector dot product itself, you always get a positive number, because if you look at this, when I dot vector x with vector x itself, I'm basically adding a whole bunch of squares together. Therefore, this have to be greater than 0. So that kind of proved property number 1. But more importantly, this expression right here, you actually have seen this before. You've seen it in chapter 1.2. So if you're going to go back to your notes, pause the video and go back to your notes and look for where you see this thing, you could. And if you do it correctly, you go back and look, you probably remember that recall in 1.2, we learned about how to find the length of a vector x. And that length is given by square root of x1 squared plus x2 squared plus dot 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 plus xn squared. So combining these two things together, put 1 and 1 together, you find out that vector x dot vector x would just simply equal to the length of vector x squared. That is an important interpretation of a dot product. Any vector dot product itself would simply just form the length of the vector square. Or, more importantly, we can now define the length of the vector to be equal to square root of the dot product of the vector with itself. So that becomes an important formula for you to use to find the length of a vector. We condense this formula right here into a much nicer looking formula. And remember, see, this formula requires people to know what dot product in order to use, and this one does not. And obviously, mathematicians would prefer this one on this side because that makes them look smart. So now the next thing I want to talk to you about will be the following. So now that we have this dot product, we know that dot product of a vector by itself form the length or the square of the length. Is there some other way to interpret dot product? Well, as a matter of fact, one of the most powerful interpretations of dot product is that we can use that to actually relate two vectors to the angle between the two vectors. So remember, two vectors are basically nothing more than just two arrows that have length, magnitude, and direction. So if you take two vectors and put them together starting from the same exact point, you actually form basically two sides of an angle. And therefore, now the question is there some way to relate that angle with the two vectors that are on either side? And if you think about it, it makes sense, because the two sides of an angle, if they point in a different direction, it would definitely have an impact as to what the angle between them is going to be. So now the question then would be how to find that correlation between them. So imagine the following. Let's say we're given two vectors. Let's say vector x and vector y. So if I simply form them right here, so let's say we have vector x, and let's say we have vector y, then it definitely forms some kind of angle in between the two. So now the question is there an association? How to find the association between the two vectors and the angle between them? So angle theta would be the angle between vector x and vector y. So the way to do that is to make use of something that you learned back in Algebra 2 and trigonometry. So as a matter of fact, I actually don't know you guys have learned it. But let's find out. So in this picture right here, notice that I do have the two sides of the angle. To actually try to find out what the angle is, I do need something else, and that something else is this. If I now form a vector, oops, sorry, it's kind of hard to get to draw a thing to connect. Okay, let's say here, right here. So suppose I have this vector right here, and this vector is, oh, actually, you know what? I'll draw the vector the other way because I wanted to use y minus. Okay, let's hope it's not going to be the next 10 minutes just me drawing this line. Okay, let's say that's it. I'm going to say this vector is vector x minus y. Now notice that once I draw this vector, I actually form a geometrical shape that we all know, and that is triangle. So in this case, since we are given vector x and vector y, then we definitely know vector x minus vector y, which is the vector that goes from y to x. And if you want to use vector y minus vector x, is perfectly fine. It's exactly the same thing in this discussion. And therefore, we actually form this triangle. Now, since vector xy and x minus y are all known, we also know the following. The length of vector x, the length of vector y, and the length of vector x minus y. So these three lengths are both known to us. In this scenario, where we know all three sides of a triangle, we call this SSS. So what does it mean by SSS? Some of you probably remember learning in geometry. It basically means side, side, side. That means that if you have two triangles and you know that they have three corresponding pairs of congruent side, the two triangles must be congruent. So here is kind of the same concept. If I know the length of all three sides of a triangle, then we have a very unique triangle here. And because we have this unique triangle, we can now use law of cosine to find angle theta. So what I don't know is whether you learn what is called law of cosines. I'm under the assumption that you should have learned how to do that in Algebra 2, but even if it's not, you might remember learning it or at least heard about it and know something about it in BC Calculus. So law of cosine is nothing more than just a very simple formula, which states the following. Okay. So in case you don't know what law of cosine is, just give you the essential. Suppose you're given a triangle where the three vertices A, B, and C, and the length of the three sides are A, B, and C. Now here's something important. Notice that when I put A, B, C there, the lowercase letter is actually opposite to the capital letter. So that's how you properly name a triangle with its side and its vertices. So you will not name C next to the angle C, but you name it across because that's unique. If you learn to name it next to it, there are two, and then you don't know which one to name. So that's the reason why we use across. So in this picture right here, suppose I want to find out how big angle C is. Then law of cosine dictate that this is true. Law of cosine basically state that the lowercase c square is equal to a square plus b square minus 2ab cosine c. So the three sides of a triangle and angle C must satisfy this equation. And some of you might notice that if you kind of simply ignore the minus 2ab cosine C, this law of cosine is nothing more than just Pythagorean theorem, and you are correct. The reason why it is just the Pythagorean theorem is because if angle C is indeed the right angle, cosine C would become 0. And therefore minus 2ab cosine c would drop out from the equation, and therefore give you a squared plus b squared equal to c squared. So that's how that works. So the minus 2ab cosine c are actually there to compensate for the angle c not being right, but maybe tilt forward or backward, and then now you can adjust the c squared accordingly. That's basically how a law of cosine works. So what we have here is this exact same situation. So what is the same exact situation is the following. If you once again look at the picture that we had before, maybe I just amend the picture up the top. So if I look at this picture right here, notice that we just have this angle right here that we're looking for. And now I can actually, you know what, let me redraw the picture. So if I redraw the picture, so here's my vector x, here's my vector y, and here's my vector x minus y. So here's my angle theta. So that angle is kind of like angle C in this picture. So now what happened to these two vectors? So this one is vector x, this one is vector y. But in the law of cosine formula, we need the length of those vectors. So I'm going to go and label that this is the length of this vector is vector x. The length of this vector is vector y, and then the length of this vector that go between x and y is the length of vector x minus y. And because of the fact that we are actually using the length, it really doesn't matter whether you do y minus x or x minus y. That's the key. So now we're ready to kind of try to figure out what's going on. So what's going on? So while using the law of cosine, I can now try to relate all these vectors together, or the length together. So the key thing about using law of cosine correctly is to identify the angle. And then whatever opposite the angle has to be the C in this formula. And then the angle has to be the capital C in this formula. So for us, theta is the angle that we're using. So the theta would be actually replacing the capital C. And then the length across from it, which is this one, will become lowercase c. So therefore, it becomes this. Length of vector x minus y square is equal to length of x square plus length of y square minus 2 length of x, length of y, cosine theta. So that become a formula that now relate the length of x, y, and z with angle theta. Now, but of course, the issue here is that we want to actually relate the vector x and y with angle theta, not just the length. And the reason why that is the case because there could be millions of different vectors that have the same length. So therefore, there could be millions of different vectors that kind of fit into this description. So we want it to be specific to the vector x and y. So how do I do that? Well, the easiest way to do that is to make use of what we know about length. So if you recall, the length of vector x squared, yeah, you're right, if you kind of have a deja vu of seeing this, because we just talked about it not 10 minutes ago. The length of vector x squared is actually just the vector x dot vector x. So using that concept, I can say, I'm going to just move it down here so that I have more room. So I can say that length of vector x minus y squared is nothing more than vector x minus vector y dot product vector x minus vector y. And that would equal to vector x dot vector x plus vector y dot vector y minus 2 these two things doesn't have the square, so I'm going to just keep them the way they are instead of introduce radical. So now what do I do with this? Well, now what I need to do is kind of clean up this part right here. X minus y dot x minus y. So how do I do that? Well, you have a property that tells you what to do. If you have a sum of between two vectors and then you dot product a second one, you can actually distribute. So that's what I'm going to do here. I'm going to say, well, just this part right here will turn into x minus y dot x minus x minus y dot y. So by basically taking this and distribute to both x and y, keeping the negative. And now both of these are just distribution again. So I'm going to distribute the vector x into x minus y. So become x dot x minus y dot x minus x dot y. Now double negative here, minus minus become positive y dot y. And that's equal to x dot x plus y dot y minus 2 length of x, length of y, cosine theta. And I know things seem like it's a lot more complicated, but it's not, because notice x dot x would just simply cancel from the left side and the right side. And then the y dot y would cancel from the left side and the right side also. And because the commutative property, that basically tells me that negative y dot x is the same thing as negative x dot y. So therefore, when I combine these two together, these two combine to negative 2 x dot y equal to negative 2 length of x, length of y, cosine theta. And voila, the negative 2 just cancel out. And now leave me with x dot y equal to length of x, length of y, cosine theta. Now this is an important formula because this formula allows us to evaluate the dot product between two vectors without knowing what the two vectors are, if we do know the length of the two vectors and the angle between them. So now you have two different formulas that will allow you to find dot product between two vectors. One is by knowing what the two vectors are, so they can dot product. You can multiply corresponding number together and add them up. That's the dot product formula we learned in the beginning. Now you learn a second formula that allows us to evaluate dot product between vector x and y, provided that we know the length of those two vectors and the angle between them. Then we don't need to know exactly what vector x and vector y are. This formula is also very important because there are two other variations that we can use. The next one is to simply solve for theta. If you solve for cosine theta, you find out that cosine theta is actually equal to x dot y divided by the length of x, length of y. So that gives us a formula that allows us to find the cosine of the angle between two vectors based on the two vectors themselves. So that's also a very important formula that you should know. And finally, the last formula is to basically take the cosine inverse of that to form the angle theta. Now, however, with that being said, it's actually very interesting to note is the following, something worth writing down for yourself. When you're looking for the angle between two vectors, the angle that you define is always going to be less than 180 degrees or less than pi. The reason being because this formula that I just wrote with the cosine inverse only return angle between 0 and 180. It will return an angle between 0 and 90 provided that x dot y is positive. But if x dot y is negative, it will return an angle between 90 and 180. Reason? Because if x dot y is positive, since length of vector x, length of vector y are both positive, you have a positive value inside arc cosine, therefore result in a first quadrant angle. If x dot y is negative, then that would force what's inside the cosine inverse to be negative, and therefore will result in a second quadrant angle, which is between 90 and 180. Unfortunately, I have to stop right here because the video is about 35 minutes long, so I'm going to stop right here. We'll continue to talk more about this formula and talk about how to use it in tomorrow's video. All right, talk to you guys tomorrow. Bye.